burns very quickly, between 5 and 10 seconds. A heavy pasture might take 10 to 15 seconds to burn. A light pasture, 5 or so seconds. They can spread very fast, can be upwards of 10 kilometres an hour. The fastest, most reliably recorded grass fire was 27 and a bit kilometres an hour, sustained for 45 minutes. That was in the Riverina. There have been reports of sustained fire spread of over 30 kilometres an hour in the Wangari fire in 2005. The thing about grass fuels are that they're open to the full force of the wind, so they're very responsive to changes in wind speed and wind direction, and because of the fineness of the fuel they can build up very, very quickly. And also because of the lowness of the fuels, they have relatively low flame heights compared to forest fuels. So the factors affecting fire spread are contained essentially in the Grassland fire spread meter. Has everybody seen the Grassland fire spread meter? Nods? No? No shaking? Good. So that meter has in it grassland curing state, dead fuel moisture content, pasture condition. And pasture condition has two components to it, one of which is horizontal continuity and the other of which is pasture condition. Fire growth, and Phil talked about the importance of the discovery of the importance of head fire width yesterday. And there's actually a few slides in here that you'll recognise from Phil's talk. And also wind speed. So wind speed incorporates the shape of the fire, and it's also given as a function of the pasture condition. So the grass curing function that's in the meter is this curve, which starts just above 0 at 50%, has its zone of greatest increase around the 75 to 90%, and then starts to tail off above 95%. So once your grassland gets to 90, 95, it's pretty much all the way there, even if it hasn't reached 100. Now the curing in the landscape is going to vary greatly in space. So you could end up with creek lines that are green at the same time as ridges that are fully cured. So you're going to have this variation of 100% cured, less than 100% cured across a landscape. The function that's built into the meter applies to uniformly cured pastures, so it doesn't take into account this variation that you might expect in curing across the landscape. And so the meter will actually over-predict when you've got landscapes less than 90% cured. The rate of spread is not affected much by recent rainfall, unless, of course, the rainfall is enough to germinate seeds underneath the dead standing annual grass, or it reshoots perennial grasses. The fuel moisture content function in the meter looks like this, with moisture content down the bottom and the rate of forward spread factor, so the multiplier by the raw rate of spread on the vertical axis. As your moisture content increases, the effect on rate of spread decreases, and it bifurcates at around 12%, depending on wind speed. So if you have wind speed less than 10 kilometres an hour, the green line will follow, and it will reach a moisture content of extinction of around 20%, and fires won't spread. But if you've got wind greater than 10 kilometres an hour, it will follow the red line. You'll actually have fires continuing to spread at higher moisture contents, up to about 24% as the moisture content of extinction. Now fire growth, as Phil said, was a very important discovery in understanding fire behaviour and allowing Phil to actually go back and analyse those fires that proved conclusively that wind played no role in determining rate of spread. This is an animation of one of Phil's gunpoint experiments from the early 1970s, where the fire perimeter has been mapped every 2 minutes. We've got two vectors here that indicate the direction of the wind. So if we run this, we can see that as the wind wobbles, the perimeter wobbles a bit. And up to this point, this is about where the work that MacArthur did looking at small fires applied. But what Phil did was allow these fires to run for a great length of time. So as these fires continued to respond to the waggle in the wind, they actually grew in width. And as they grew in width, they actually increased their rate of spread. So when this was plotted on a graph, what Phil found was that in that first 20-minute period, a steady state rate of spread had been achieved for the size of the fire that was there. Wind speed was about 6 metres per second. But then as the fire continued to grow in size, it increased its rate of spread, and it did that in a series of steps as the width increased. Now the wind, you'll see here, didn't actually increase an awful lot, but the rate of spread continued to increase, and that was put down to the fact that the fire was getting wider. And here's an illustration, one of these Phil showed yesterday. So we've got 3 fires being lit at the same time. There's a point ignition up there, 50 metre line and 100 metre line. This is 40 seconds after ignition started. A minute later, you can see the point ignition hasn't really spread an awful lot. The 50 metre line is only slightly slower than the 100 metre line. A minute after that, the width of the spot fire has increased substantially and the shape of it has become rounded. The width of the 50 metre line has narrowed and has become very pointed, and the 100 metre line has just taken off and reached the end of the block. So we've got clear evidence here showing that the size of the fire makes a difference to its rate of spread. And this is encompassed in this graph here, which needs a bit of explaining. So basically this graph shows the width of fire required to reach a maximum potential rate of spread for 3 different wind speeds. We've got a wind speed of 7 kilometres an hour. The fire needs to reach about 25 metres wide in order to reach its maximum potential rate of spread for the conditions, which is about 1.5 kilometres an hour. At 14 kilometres an hour, the fire needs to reach about 100 metres wide in order to reach its maximum potential rate of spread. And at 21 kilometres an hour, that width is up to around 150, 175 metres. What this means is that if for any reason the fire is kept narrower than what it needs for its potential rate of spread, it will be spreading slower than its potential. So if you've got 21 kilometres an hour, the model's going to be predicting 7 kilometres an hour, but if it's only 25 metres wide, it's going to be spreading at 4 kilometres an hour. So if there's a change in wind direction, but not wind speed, and a flank suddenly becomes the head, it's immediately going to be spreading at 7 kilometres an hour, almost doubling its rate of spread just with a change in wind direction and not a change in wind speed. Pasture conditions. So here are the 3 categories that were used to describe pastures in the metre. So we've got a natural, which is an undisturbed or at least very lightly grazed natural grass. We've got a grazed grass here or mown. In some way it's been modified, and you can see the culprit in the corner here. Common condition in South East Australia during summer. And then we've got an eaten out pasture here, very heavily grazed, generally less than 3 centimetres tall, but the important bit is that it's now becoming discontinuous. There's scattered patches of bare ground. And you can see here a fire has tried to spread through this and failed. There's bits where it's just gone out and not been able to spread continuously. Now Phil showed this picture yesterday that illustrates quite convincingly the lack of importance of fuel load in determining rate of spread. So I won't go into this in any great detail, but the wind speed is the same in both. Fuel load is about half and the height of the fuel is about half, but the rate of spread of that fire is about the same. So even though it's got tall flames, compared to this one here, it's not an important component of determining how fast that fire spreads. But what it does do is allow it to overcome breaks or gaps in fuel. If we go back to the start, there's a really cool picture of what can happen with tall flames and a 2 metre bare break that allows tall flames to actually enable the fire to cross those breaks. So that aspect has been built into the model by giving a slight increase in the rate of spread for the undisturbed or natural pastures compared to the grazed. And it's about 20% is what's built into the metre. Fires in eaten out pastures spread at about half the rate of spread of the grazed pastures. But the important bit here is a threshold wind speed. In continuous fields, you need at least 5 kilometres an hour for a fire to spread forward continuously in a consistent manner. When the wind speed is less than that 5 kilometres, the wind is described as light and variable, and you can get fire spread in any direction and not consistent. The threshold required for fire spread in fields that are becoming discontinuous increases with the amount of discontinuity in the field. So in an eaten out pasture, as an example here, you might need a 10 kilometre hour wind in order for that fire to start spreading. But as soon as you get above that threshold, your rate of spread is immediate. It doesn't go through a growth or acceleration phase, you immediately jump up. In more discontinuous fields, and spinifex are a great example, that threshold can be quite high. So you can be waiting for 15 or even 20, or even 20 kilometres an hour for a fire to actually start spreading forward consistently. And so in a 47% cover spinifex, the fire will start spreading at 15 and will almost immediately be spreading at 3 kilometres an hour once you get to that wind speed. Below that threshold, you don't get any rate of spread at all. The fire just won't spread. Backing rate of spread. What was found was the backing rate of spread of the fires is fairly independent of wind and is actually a function of dead fuel moisture content. And so at the maximum backing rate of spread is going to be about 30 metres an hour into the wind. Erratic fire behaviour. So we've got a number of components: wind, topography or slope, and combinations of the two. Now, Robert's talk this morning talked about the boundary layer. Here's an illustration of what the atmospheric boundary layer looks like, where you've got the top of the boundary layer defined by the difference between what we call the geostrophic wind and the air below that's actually affected by the surface. So you can have thermal heating of the ground that will cause convective bubbles to rise. That can intrude into the geostrophic wind layer. That can actually bring down very fast moving air into the boundary layer. That will form large eddies which will then cascade down in size as they break up to the point where they're now interacting with the ground. So these eddies will actually form gusts and lulls, and they're the things that are going to be affecting the rate of spread of fires in the open here. Things like trees and other structures are going to create mechanical turbulence, which are also going to create relatively shorter-lived eddies and gusts. And here's a map of what this might look like if you were to stick out a row of anemometers into a field and measure the wind speed. This is actually over water. This is an illustration from a yachting book where the rate of the wind speed has been plotted here in kilometres an hour, showing very much a topographic type structure where you've got a large gust here, gusting up to 85 kilometres an hour, and just behind it a lull down to 50 kilometres an hour. But it's highly spatially variable and highly temporally variable. Here's a picture from the Western District fires in Victoria in 1977, showing highly turbulent winds in wind speed. So minimums around, what's that, 15 knots, gusting up to around 50 knots or thereabouts. But also changes in wind direction. So you've got massive changes in wind speed and also massive changes in wind direction. It's these changes in wind direction that are going to drive the growth of fires. Here's some illustrations of the effect of these eddies as they flow across the ground. One eddy that's got a speed of 8 kilometres an hour imposed over a 20 kilometre hour mean wind flow will result in a 28 kilometre hour gust hitting a fire. If the eddy is rotating the other way, you can end up with a 12 kilometre lull. Mean wind speed is still the same, but you've suddenly gone from 28 kilometres to 12 kilometres just with the passage of an eddy. And these things can change wind direction. There's a downburst here. You can have updrafts, you can have downdrafts as these things are moving across the landscape. And here's a good illustration from Anavaru grass experiments in the 80s, showing a downdraft on one fire and an updraft on the other. Downdraft is acted to increase the width of the fire and therefore the rate of spread of that fire. The updraft has narrowed the fire and slowed it. Distance of 200 metres. So, topography. Now this is a fairly famous graph, lots of people have seen. This is out of MacArthur's leaflet 107, showing slope effects, and on the positive side, doubling the rate of spread on flat ground for every 10 degrees. On the negative side, you've got a straight line that goes to about half at 10 degrees. Now I've done a little bit of work here to actually improve the prediction of this mathematically. The current rule of thumb has been implemented by Noble, Barry and Gill as being for every 10 degrees downslope you halve your rate of spread, which means you follow this orange line and it gets very, very low very, very quickly. We've developed another negative slope function called Caterburn, which actually matches quite a lot of experimental data that's been collected around the traps over the years, and also much more closely follows MacArthur's original line, but allows us to extend that beyond 10 degrees. And that asymptotes eventually to about half the flat ground rate of spread. Here's an illustration of airflow over a hill. Two possible options with airflow over a hill. One is you get streamwise wind flow, in which on the lee side you actually have airflow down the hill. Same hill, slightly different conditions possibly. You could have what's called recurve wind, where the wind actually separates from the top of the hill and results in a lee eddy with wind flow up the hill. So this has major impacts on determining what's actually happening in the lee of hills. The other important thing to be aware of is on the windward side of these slopes, depending on the atmospheric stability, you can get a lot of acceleration on airflow on the windward slope. So, in summary, some key take-home points for those people wanting to predict grassland fire behaviour. Grass fires can respond very quickly to changes in wind speed and wind direction, and they can spread very fast under strong winds. There's no effect of fuel load as such on rate of spread, but fires in natural or ungrazed pastures will spread slightly faster than fires in grazed pastures. The taller flames that result from these taller fuels will enable the fire to cross breaks in the fuel easier. And overall, as I said, it's about 20% increase in the rate of spread. The fire spread meter will over-predict when fires are small, because we're assuming that a fire has already reached the minimum width for its potential rate of spread, or it's restricted in its growth, whether that's from suppression or running up against a fire break or something. And it will also over-predict when the landscape grass curing is less than 100% and not uniform. One of the most important things to remember when using the fire spread meter is that the best results are going to be obtained by using mean input values over a period of about 20 minutes, because what you want to do is try to incorporate this gust and lull structure into a mean value, because the model is going to give you a mean rate of spread for a considerable period. You won't ever get the instantaneous rates of spread given by the maximum gusts and lulls out of this wind structure. So averaging the wind over 20 minutes will get rid of that structure. You can also average over a distance if you wanted to incorporate the spatial variation in such things as pasture condition or grassland curing. And these will give you your best long-term mean rate of spread out of the metre. Thank you.